Hi guys, welcome to the video for chapter 5.1.3. Today we're going to be looking at charges flowing in a conductor. So we've got 4 learning objectives today, and actually one of them was a learning objective that I had missed last time. So let's jump right into this. So this first learning objective is actually a review from chapter 5.1.2. And it asks us to show how a volt is equal to a joule per coulomb. So we already know that a volt is equal to the work per unit charge. And so the volt itself over here is equal to, so the unit for voltage is, or potential difference, potential energy is joules per coulomb. Okay, so that's essentially what we're really talking about there, right? So electric potential at a particular location. All right, so on to the new stuff for today. Learning objective number 2, show how an amp is equal to a coulomb per second. So again, we're sort of focused on a formula here, but let's maybe first look at a few definitions in order to understand the whole thing. So we got to define a few things here. The first thing is, what is an electric current? And I mean, electric current is essentially a flow of charge or charged particles, okay? So charge here can refer to charge carriers. So you might see it referring to it as charge or charge carriers. And charge carriers are essentially particles that move and have a charge. Okay, so for example, a proton or an electron. And so the electric current, I, is the number of charges flowing past a material or space in a given time period. So as a result of that, the current is charge per unit time. And so usually we do charge per unit second. So usually we measure it every 1 second, but we can measure it over larger periods of time, like maybe every minute or every hour. And so this is a quick little summary of the formula there, where I is the current, Q is the total number of charges, okay? Or sometimes we refer to it as the net charge passing a particular space or material. And time we already know is a time interval, usually measured every second. So we talked a little bit about charged particles before. The term was charge carriers, okay? So charge carriers or charged particles can be a proton, an electron. It can even be an alpha particle, okay? Or it can even be an ion. Okay, so every one of these things are charged. But of course, they cannot and they should not be things like photons, and they should not be things like neutrons, okay, or atoms that are neutrally charged. So it could be like isotopes or things like that, but just like your regular atoms that are not ions, okay, so these are non-ionic ones. Okay, next up, so charges can also flow as a single particle. So you might see questions where there is one single particle flowing through. There might be a collection of particles, such as a beam, or they might refer to it as a stream of particles. So there's quite a few things, but the idea is that there's a continuous stream or beam of particles flowing through. Charges can also flow through different matters and substances, such as solids, liquids, or gases. Okay, so there's things like conductive gel, copper wires, and things like that are certainly one of the most common conductors of electricity. Okay, so on to our third learning objective now. So, sorry, that was very quickly. There's a little bit more information there than what we really needed. We really were looking at how an amp is equal to a coulomb per second. So we went a little bit further than that, but that's all to help you guys understand. This is quite a holistic thing. It's incorporating a lot of the knowledge that you've already learned. Okay, learning objective number 3 is to discuss the nature of metals and charges within them, explaining why they are good conductors. So they is referring to metals. Okay, so why metals are good conductors. So first off, when we're talking about a material being a conductor, we can apply a potential difference across 2 points. Okay, so we could apply it across a conductor. We can provide it that across an insulator. An electric field will form in between that. Okay, and any charge carriers in the field will experience an electrical force. So this is the Coulomb force that we talked about way back, right? So if you remember Coulomb's law, right? F, K, Q1, Q2, R squared. This is the Coulomb force, right? And we talked about electric fields being related to the Coulomb force as well. Okay, so we're incorporating everything that we had learned all together right now. And this force is causing charge carriers to accelerate. Okay, so charge carriers have a mass and they are affected by a force. They will accelerate. Okay, so remember, those charge carriers may be protons, they may be electrons, and if they were an alpha particle, they would actually be also the neutrons as well. So because the neutrons are tied together in the alpha particle, we have to consider the entire mass moving, even though the neutrons don't experience a force. Okay, so using electric potential difference, sorry, let me just back up here a little bit for electric potential difference. So imagine that we have like the big charge here. Okay, so over here we might have something like 500 volts, and then over here we might have 400 volts. Okay, so the electric potential difference in this case would be 100 volts. Okay, so it's very similar to the idea that there's an electric field here. Actually, there is an electric field, but it's being applied over an actual substance this time. Okay, and so at one end there will be a higher potential, at the other end there will be a lower potential, creating a difference. Now, a conductor is a material that allows mobile charge carriers to move with a significant net translational motion when an electric potential difference is applied across the material. So we're going to jump into a very quick chemistry lesson here to talk about this idea of net translational motion. So significant net translational motion. So actually, I'm just going to jump down here a little bit to this particular diagram here. This is actually very helpful because in a natural state, objects are still vibrating. And so in this natural state, the electrons and even the protons will still be vibrating and moving a little bit. Okay, and what we're doing is when we apply an electrical force by having a potential difference of voltage, right? So the electric field, the potential difference will provide the electric field. The electric field will generate a force. And that force will act on charge carriers, which are our electrons. And so those electrons, you can see the bigger arrow indicates a larger magnitude, and they will be pushed in a general direction. So this is for conductors. Okay? For insulators, there is a large amount of resistance, which is holding the electrons in place, and it's preventing the motion even under the effects of an electric field. But that's getting a little bit further than we need to talk about for today. But I just wanted to briefly mention that in case you were thinking about, well, what happens about insulators? We'll be talking about that, okay? Now, why do metals make such great conductors? Okay, and it's because metals generally want to give away their electrons to become more stable. And so I wanted to quickly talk about that. And to do that, we need to look at electron orbits actually. So I'm just going to do a quick Google search for electron orbits in metals. So metals, if you studied the periodic table in maybe a chemistry unit, you might have learned that metals generally have a few electrons in their outer orbit. Okay, and what we're trying to understand, I wanted to find something a little bit more simplistic for students. So maybe this will provide us that. This is a little bit too complicated. Unfortunately, the diagram isn't working properly in here in this. But normally speaking, what we're really trying to say is that most of the metals generally have only a few what are called valence electrons. So especially the alkali metals, they contain 1 to 2 electrons on the outside. And this has, generally speaking, if you compare metals to something like noble gases have 8 electrons. And that is a number of stability. So a lot of metals, a lot of substances want to be like a noble gas because the number of electrons tells us that the material itself is stable. Okay, and so a lot of what chemistry is about the transference of electrons from metals that generally want to give away their electrons to non-metals who want to take on their electrons to make up the number 8. So as a result of that, because most of the metals only have 1 to 2 electrons, they tend to give them away, which gives them what we might call an ocean of electrons. So that can sort of be imagined here, where the blue dots, I'm just going to use the blue color here. So the blue dots represent electrons, and the red dots represent the protons. And so the protons don't generally move, but because there's so many electrons that are able to move, that makes them really, really good charge carriers. Okay, so there's an abundance of charge carriers which are willing to move around. Okay, our last learning objective is a little bit more calculation based. So all of that was very much theory based, and we're going to do a little bit more theory coming up here. So the idea of the drift velocity is that a drift velocity is essentially it's related to the idea of net translational movement, which means the movement of the particles is not random anymore, but that it's actually moving into a general direction. Okay, so drift velocity, it's drifting in a particular direction. Okay, and usually, and we might even say with purpose, okay, due to a force acting on it. Okay, so to really understand everything we've talked about, here we actually have a copper wire, maybe, a wire, okay? So this could be any wire, but usually it's copper. Okay, so we have a cross section of a wire. So we have the area of the wire. This is the length of the wire. So D is the length of the wire. But we're re-representing the length depending on how fast the particles are moving, also known as the drift velocity. And so how fast they're moving in a certain period of time, so change of time. And so we've got 10 electrons moving in a particular direction across this section of wire, okay? So this will form the basis of a formula where we're looking at the number of charges, n, moving through an area or a distance. So altogether, this forms a volume, right? That times that times that. And so that's the magnitude of the charge. And usually this is the elementary charge, 1.6 times 10 to the negative 19th. So I've got some notes on the side here to represent what I've been talking about. okay? So the number of charges multiplied by the charge that they carry along with the volume that they're moving through, okay? So that is what we call our delta Q, okay? The change of charge per unit time in a current. Another thing, sorry, this is so jam-packed with so much information, guys. Another thing we want to talk about is something called conventional current. So you might have remembered that the proton was first discovered, hence the word proton, was one of the first atomic level particles that was discovered. So we didn't discover the electron until sometime later. So as a result of that, physicists or scientists first thought that it was the positive charge that was moving. And eventually we discovered that it was not the positive charges, but it was in fact the negative charges that were moving. So when you see the word conventional current, this is referring to protons moving from a high positive potential into a negative voltage or lower voltage area over here. Okay, essentially everything we've been talking about in fields. Okay, when they use just the word current, they're talking about electrons flowing. Electrons will always flow in the opposite direction of conventional current. So you'll always be given, if you have to know the direction of things, they will always tell you either electron flows from left to right, or conventional current flows from right to left, maybe. Okay, lastly, what you might also be expected to do is to connect these two formulas together into a slightly different formula. And so you can see that there is a connecting variable between the two, delta Q. Delta T also connects the two, but we'll see what happens there. So when we connect delta Q, so essentially we have change, the amount of charges, and then we have the rest of this formula. And then we also have current multiplied by change of time. So since these two ends, this end and this end, are also equal to delta Q, we can sort of eliminate this guy in the middle. And we can say this now equals this. And the good thing about this is that you can eliminate change of time because they exist on both sides, which now leaves us with our new equation. Current is equal to the number of particles moving through a volume, or a volume of space. So this is also going to be one of the formulas that we'll be looking at in our example right now. So copper is, in its metallic state, has one free electron and a bulk electron density of 8.46 times 10 to the power of 28 electrons per meters cubed, okay? So within a meter cube of space of copper, that's how many electrons there are, 8.46 times 10 to the power of 28. And now what we're seeing here is that there is a current that's flowing through a copper wire, or a chunk of copper essentially, and that has a radius of 0.5 millimeters. Okay, so we're going to start putting all of this together, and we're asked to determine the drift speed. So what I'm going to do first is I'm going to rearrange the formula to isolate drift speed onto one side. And so we're just going to do our substitutions. So 1 amp, number of electrons. I'm just going to do a lazy thing here and grab this whole thing. So I'm going to paste that. So that's a number of electrons. And we're going to specify the area. Now we have to be careful because this is the radius, not the area. So to get the area of a cross section of a wire is pi r squared, right? So we're going to do pi. The radius is 0.5 millimeters squared. And lastly, the charge is the elementary charge of a particle. So that's 1.6 times 10 to the minus 19 coulombs. So once we complete all of our calculations, we're going to get, sorry, let me just check out the calculation here. We're going to get 9.41 times 10 to the minus 15 meters per second. Okay? So we're making use of the new formula we just formulated and performing calculation of that. You might see the question in different formats, but overall they're going to be roughly the same. Okay guys, that's the end of this video. There are some questions that I've posted up on Google Classroom already, so make sure you guys check those out. There are 3 questions at the end of Cognity, which I would really encourage you guys to try out as well. So I'm just going to show you guys where that is here in this video. So it'll be chapter 5. And there's an end of section question. So I'm just going to scroll. So here, there are 3 questions here. Question 1. And then there's question 2. It's showing you the answers, obviously. But so you can hide that or show that for yourself, okay? All right, guys, good luck. There's a lot of stuff that we covered. So do take the opportunity. If there's something that you want a further clarification on, make sure you guys send me an email or leave me a message on Google Hangouts, and I'll do another video for you guys to hopefully clarify some of those things, okay? It will take some time for you guys for the material to sink in, so make sure you take some time to review this. Thank you guys. See you later. Bye-bye.